Hi everyone. In this tutorial, we are intending to continue from where we left the last time. So we have covered the basics on what we intend to do using the RAG, that is Retrieval Augment Generation. This is something that we are going to attain by using the code in the session. We are going to use Windsurf IDE, that is an intelligent AI tool itself, wherein we can use the provision to use chat, and using that we can get our query resolved. This is one of the intelligent ID we have. Along with, we have some other provision like you to use cursor. That's another ID. So coming back to the context, in this example, we are going to use one of the document that will be stored, as we have discussed earlier in the previous session, as a embedding using the embedding model. And once that document would be saved as an embedding, we'll be making a call using an LLM, what we refer to as a prompt, and we'll be getting the response based on the embedding we had defined. Now, before we go to the code, we'll talk about the basic terminology we are going to use here. So to start with, okay, so there are certain things like in LLM. One is called token. Token is nothing a subword piece of text. For example, if you see here hello world, it can be taken as hello, comma separated, then world separated, exclamation separated. So it's basically the more the token or LLM model will be able to support, it's like it will be able to break into different permutation combination of the sentence, and it will be able to identify the context more precisely. In other words, we can say it, the more the token model supports, it's like it can do the query expansion. For example, if you ask a question, how's the weather today? So it will break into different chunks, like how is the weather today, or today how is the weather, or how it's going to be the weather. These are some combination that it will create, and based on that, our LLM will predict the answer. So coming back to the exact terminology here, it's called token. It's like the way it can, the model has a provision to break the input to get the context of the question a user is asking using a prompt. And now another word is embedding. Embedding is nothing but a vector representation of a token or sequence of token. For example, if you see, the token hello can be represented as 0, 0.1, 0.2. So as if you see here, whenever we'll be running this example, we'll be getting the numerical representation of the text that we are going to store as an embedding. So whenever we are referring embedding, we can visualize it like a database or the data source where we'll be storing the text in a numerical representation. Similarly, we have an embedding model. So embedding model is nothing a machine learning model that maps text to embeddings. For example, I've just seen how the representation is done for each text. So the next one is similarity search or the vector search. So as we discussed, a vector representation, it's like for any text, if you say any database entry, if you say, it will be stored into numerical representation, and it will be visualized as a value in an n-dimensional space. So based on the embedding, the particular position would be determined in n-dimensional space and would be used to determine the similarity of the question to the probable answer. That is the crux of how the RAG will help us to predict the answer. Now, question might arise like, how might it help? Like, we can store it's as good as storing in a database. But the point is, in case if you have an object that is high dimension, it's not easy to store the data as such in database. Considering if you are going to save a PDF, we can save as a PDF as in one of the column as a blob object in the database. Eventually, you have to do the search across to figure out the answer, or you have to pass programmatically. But here, the whole text is considered to be broken into different n dimensions and would be stored itself, corresponding to each relevant word that comes into the text. That is something we'll be covering in the next session. For it called LLM context window. As we just discussed, the higher context window means an LLM can accept more relevant information to assist with the query. It means if a model supports a higher context window, for example, if it supports more token, it means a question or a prompt can be broken down into different logical meaning, and that will help us to get the response from the database and jolt it and get the more precise answer. This is more like if you see in a RAG pipeline, the one we are going to do, if it has more context window, it will give you more reference items. So we'll get more predictable, more precise answer. So basically we can say proportionally, the higher the context window and LLM support, more precisely we'll get the response. So if we talk about, if we are using Mistral AI, we are using ChatGPT, and oftenly we keep on hearing like GPT-4 is more profound, or Cloud version is more profound. Now the DeepSeek model is giving these many tokens. So this can be visualized like all these models with the time are able to give you more the higher context window. So any question being asked by end user to LLM as GenAI, in a GenAI setup, it's able to get the more context and more precise answer based on using the tokenization of the input given by the prompt. Now, what exactly the prompt is? Prompt is nothing but common term that describes generative LLM. For example, for the end user, we are always giving input as a text-based, and that will be understood by the generative LLM. As we just discussed, it will identify what exactly the question is being asked into, in which context. For example, if we ask fits, now fits, it could be something that is a library in Python. It could be something deal with the sports, or could be something related with the cold drinks. How a LLM model understand what it actually means. So making a model understand the actual meaning of a question being asked in a prompt is called determining the context, and that will be help. That would be easy to figure out if the prompt is also written very precisely. So combination of a prompt being well written prompt and a model supporting LLM, larger LLM context window will help you to give the precise answer. So if you see here, we have generated one annual report PDF. So this report, if you see, we can see here. Okay, this will open in another format. What we'll do, we'll go to the location and I'll just walk you through where the PDF has been hosted. So this is something in a location. Okay, let's see. Okay, we'll see it here. It's into my desktop AI, Mr. AI. If you see here, we have some of the example I was trying the other day. Now, if you see here, we have human nutrition. This is annual report that we are going to parse. So this is basically the annual report given by TCS. So this is our source data. So our end goal is like we'll put this PDF we'll put it into the embedding or the vector data source. That's so that all the text we see here will be represented or broken down to their corresponding numerical representation and would be stored in database, and that will could be visualized as a vector and dimensional space. So similarly, if you ask a question that is something relevant, that is something very makes a sense logically for end user, he can just put that in a prompt and its answer would be determined based on the combination of the context and whatever is the nearest similarity search would give as a part of embedding. Or we can rephrase it. The whole PDF would be first converted into embedding model. Using embedding model would be converted to numerical representation and saved. Now when the forthcoming a question is being made by the end user or through a prompt, it will generate another corresponding embedding, and the similarity between the embeddings will be determined in n dimensional space and we'll get the answer. So coming back to the code, You see here, now we have seen the PDF. Now what we do, we are just checking whether it's in the path. If it's not, we're getting it from the source. Followed by, we'll be just cleaning, we'll be replacing the new line with the, we'll be just formatting the text, cleaning the text. And then we'll have a API if it's being used to open the PDF file and just convert it into, like we say, if we're parsing the document and putting it into one of the specific in a response type, basically. The data type here defined as pages and text. So now we in order to understand, we can just run the sample of using K3 any value. So we'll just be able to print the sample. That's not relevant. It's relevant though. We need not to mandatory to use this just to visualize while running the playbook or the Python file. So then post we'll be using pandas to parse the data. We have a data frame. So data frame would be used to parse over whatever data we have uploaded using PDF file. As of now, we are just using NumPy pandas to parse the source data. That would be converted to embedding and would be saved into the corresponding vector database. Now we are using Spacy library here. Spacy is something, it will be using the module or the library called English. Using that, we'll have we define the NLP. So NLP will add a pipeline. These are all our Python library. This like we already always have provision, but the only thing we need to ensure, like with whatever the version of Python we are using or the library we are using, the directive structure might change. So we might have to see like which method is being hosted in which module. Based on that, we have to do the import here. For example, here we've done in line number 92. Now for illustration, we just see, okay, NLP, we are converted to doc. We are seeing, okay, it's being sent into 3. It's like the document that we're breaking into 3 different sections. Like this is the sentence 1, this another, and I like it. These are in total 3 sentences. Just to visualize how it will break into embeddings. Now this is the main point here. Since we have already passed it the data and cleaned the data up here by this method where we were parsing and using the PDF Python PDF library TQDM. So we got the data here, and once we passed, we are iterating these items, and whatever the data we have sent, we are converting to sentences, and based on sentences, we are passing sentences further. And if you see, this is nothing but we are just parsing it and putting to one of the data type of items that we have specified here, and we are parsing pages. So so it's something like we are just defining the split in which chunks we need to break the input file of PDF that we've just seen about annual reporting. These are the configurable things. By changing the number of chunks, the response might vary. That we'll check at the end once we are done the whole walkthrough. Now, if you see, we are splitting the list. So splitting the list here is basically, since we have already got the test data, now the test list is nothing but the list that taking here, whatever the data we have broken. So if you see here, we are just converting it into slicing into different chunks, and we are splitting that into different individual lists. Whatever the response we get, that will be stored into test list, sorry. So going further, we'll be like iterating again and just putting it at item level, loop through each pages and text whatever we get into chunks. So since in the first step above, we have broken the whole data of the PDF into chunks, then from the chunks, we are taking the pages and the text that is already separated. If you see the page and text here, we are looping it again. And this for a sample, just to see the sample. If you see here, we are seeing the embedding. If you go back down, when we run the playbook, we are seeing all these embeddings here. So in between, we have samples. If you see, sentences are embedded one by one in a list. If you see here, this is something coming from okay, maybe my search is not very precise here, but if you see here, we are printing. Okay, after uploading, we are printing here. Yeah. So here we print out our sentence splits. So we are splitting it into, like for this particular sentence, we are getting these embeddings. So the sentences is broken in n-dimensional space with these values. So each word or whatever chunks we define, based on that, the numerical representation turns out to be this way. Similarly, like for the other sentence we have done, like I like horses. So for a sample, for illustration, we have kept it here. Yeah, this one. So now I like elephant or something like we have. Okay, so if you come down, similarly, these all, it's just showing the sample, random sample basically. This is the size of data frame, 768. Yeah, now if you see here, you've got a sentence chunk done. This is the progress part we are seeing by using the library fits. Fits the library used to visualize. Okay, coming back to the point wherein we break the sentence already, then we have the list item. Whole PDF was broken into item was based on the chunk size we have taken, that we have defined in the above in the syntax. We are breaking to another chunks, and that is being further broken down, and we make a new join sentence chunk, and based on that we'll get the character counts or word count or token count. It is something that is configurable. And once we print the need, now if we see, we'll be printing what the length of page and chunks shows to us. We'll just check it out here. Let's see, okay, we're printing this size. So if we run this again, see here in the step, the PDF file has uploaded, chunks has been broken down. These are 3 sentences we are given as an example above. Then for all it's showing, okay, all this has been processed into the numerical representation. Now before printing the size, now in the print statement we see we have got 28 token count, so we digital transformation. So if you see from the PDF, this is the one text that got converted to this representation. Similarly, we have another one. Like this, chunks had been broken down and they were further created into their numerical representation using embeddings. So once that is done, we are using torch library here and sentence transformer model. So this is our embedding model that we are using. The inbuilt embedding model, that's all MNet based V2. And specify the device on which device to use. It could be GPU, but we are using local, so it's specified CPU. And this again for illustration we have given here one example for sentences, and this is like if you call the method and encode method will encode the embeddings. So this just while we are running, this would be helpful if we put this in chunks into a playbook or into the notebook.pny file. There we can just keep on printing into each cell, or maybe we have revision here also. But in playbook we can run and print. That will be easy to debug. From a Python perspective, these printing steps we can skip or we can omit here. Now this was a code that's being pulled into Python, but this is something print statement can be omitted just to keep in terms of to keep codes small and simple. So here also it was one example, embedding model calling and encoding this one. And if you see here, we'll just try to print how the representation for the cow looks like after adding the size for cow example. If you put it here, so suppose you put it like this. Now we'll try to run it again and we'll see how the embedding appears for the cow. Again, we see it broken into this one. We're seeing the counts. We got the representation of embedding. Now embedding are getting created, and this progress we are seeing through the fits library that we have used here in the top. Coming back to so it's still in progress. It's breaking into the token and showing the progress as well. So what we are intending to see, how the transformation looks like when we have done for the example cow. So these are just like it's just for printing into PNG file, but see here also we can run individually like a cell. That also is a provision we have in WinServe. Let's see by that. In the meanwhile, the embedding gets created where we ended up. Okay, so after embedding the size, so we need to see if I give my favorite animal in is the cow, how the embedding appears, the backend. Similarly, we'll specify the tensor, the which device to use, device is specified as CPU. So actual conversion will come here because we have already got the text chunks. We are passing, encoding, text chunks, nothing, item, and this one for item in pages chunks over minimum length. So what this value basically is, this is the value we are getting by converting, by parsing over the data frame that we iterate based on the check of the total token because we have specified the number of tokens. So we specified the number of tokens. Based on that, it is being converted into, like we can say, it's being partitioned to get the number of chunks for minimum token length. Token length we have specified already. That we can say the token count is here divided by 4. So one token is being taken as equivalent to 4 characters. So if I give a word, say a 4 word like a name, NAME, so it will be represented as a numerical representation 1. Like you can say this representation is corresponding to 4 characters. Now, if we come down, it has the embedding is done. Okay, so if you see here, this is what we are looking for. After embedding the size for cow example, so cow example we have seen here. Yeah, so after embedding the size for cow example, so this is the statement for which we got this much a big embedding. So you can say one character, 4 character been broken into different representation. And then the question would be why we have got only, like you say, if we break this, a character of 4 corresponding to 1 token. Why we're having these many representation? This is something based on the how many token it supports the model. So the permutation has broken the sentence into those many representation. Like my favorite animal is cow. It could be rephrased like cow is my favorite animal. I like animal I have seen. Or it could be phrased like which is my favorite animal? Yes, it is cow. So based on how many token the model supports, we get different permutations and we create a corresponding embeddings. And those embeddings are what we are seeing so many now. So down you see, after representation, what we have printed, and then we printed the minimum token length. So this is the token length here. And if we further break down that using data frame, now if you see, this is where we are checking it out. So once we broken the PDF into the tokens, then based on the size of the token that we defined for 4 characters, 1 token, then we converted it into a data frame that we have saved and putting it into CSV file. If you see the CSV file, you will see the representation of our chunks. These many chunks we have. Means chunks corresponding embeddings. Like for each break of PDF, we've got those many embeddings. And similarly, this is the one basic how it works. Embedding, once it's done, we are loading it again. That was just for verification. We convert it to CSV. We might not, it's not mandatory to put it into this, but this is for illustration how it gets saved. So we can debug and verify the whole flow. Because eventually, if you see here also, we are reading CSV back again. Once we are done with the data file, again, we are just putting into a list. We are seeing, okay, this is what the response we have got. Now, the part of training the data, that's PDF file, we initially talked about the PDF file about the annual report that is being trained and stored as embeddings here. And now when we are asking the question or a prompt, as of now, I have hard coded here good for protein is one that I have. Sorry. Yeah. So here till this time, this point, it's like we are done with the embedding. Now, here I'm asking question, please summarize overview of the fund invested. So this is my prompt. Like for the end user, suppose if you want to host this application, we'll create the we'll remove the print statement, we'll put into a Python file, and we'll host it on, say, on a fast API, and end user will be given a prompt in a real time in a UI or through any endpoint. He'll be supposed to ask a question, and suppose we can impersonate that prompt here, because I've just hard coded for the illustration. We'll put a query here. Summarize the fund invested. It's making a query, and what will happen to this query? If you see here, this query is the dot product is being taken for that. So when it loop through, so if you see here, we have a question. Okay, if you see, we're printing the query and then we're getting the results. So we are getting the dot products, and based on that, we are getting the response, the score and index. So whatever response we will be getting, we'll be storing in terms of the different scores. Like the more the score is, we'll get more precise answer. If you see here, 0.5, 0.83, it looks more confined and very taking only the very relevant numbers that a person must be interested to know about. Please summarize the view. If you see the value, you'll be seeing this particular probably. Okay, closure of facilities. If you see, we intend to run this one, and we go back to our location we have where we have the file. So if we are seeing the answer, it is composed out of this context from the file itself. Now suppose if this is being reconciled, question might arise, okay, we are not finding the exact answer, what we are seeing in the response, the exact statement. But that is something, once we get the response, that response is being jolted by intelligence of the AI and is rephrased as an answer. But if the reconciliation is done, we'll be able to see the exact meaning out of the answer and whatever is being there in the PDF. So this is something like based on the score, we can conclude like, okay, this is the particular response I want to go ahead, but we keep a provision of giving multiple scores so that, okay, person might not be interested only to take the very most relevant idea, a very summary. Might be for an end user, some summary means like, okay, he needs some more details. So that's why I keep a provision to have at least 4 to 5 the responses with different variation score, but the best summaries for this score. 0.8. Hence we conclude this session basically, but this is some same thing. Now this can be used as a template, like instead of a PDF, if I put in some other file, you can train that as well, and we'll get the response too. So as a part of this session, I'll conclude it today here, and going further, I'll come up with more example where it will keep it a very plain Python file, and along with MCP, we'll be showing how an MCP concept can be integrated with RAG and how we can scale it across the different sources. Thanks for being there, and I hope we'll be able to get some more insights on this from this tutorial we had. Thank you, everyone.